Everyone knows that pH is a measurement that tells you how acidic or how basic a solution is. And most people know that the pH generally goes from about 0 to 14. And so when someone says a solution has a pH of 6, that's telling us that the solution is on the acidic side. Neutral is right about at 7, so therefore anything below 7 is considered acidic, anything above 7 is considered basic. Now, what most people don't realize, though, is that the pH is actually a measurement of how many hydronium ions there are in the solution, or it's a measurement of the concentration of hydronium in the solution. The only weird thing is that it's a logarithmic, yes, I said the word logarithmic, measurement where the pH is actually equal to the opposite of the log of the concentration of hydronium. Now, before you get paranoid about the word log, which I think everyone learned in math class, the word log basically means, this is base 10, the word log basically means what power is 10 being raised to. So if you have the number 100, that should be equal to 10 to the second power. The log of 100 is equal to 2. If you have the number 1000, then obviously that's equal to 10 to the third power, and the log of 1000 is equal to 3. Now, the advantage of logs, or as a log scale, is for one, it shortens what you have to write. The log of 1000 can simply be written as 3, and the log of 100 can simply be written as 2, and it's a logarithmic scale. There are a couple other logarithmic scales that you probably know about. One that measures tornado force. Hurricanes are also measured in tornadoes, are measured in terms of a logarithmic scale. Decibels, which is a measure of sound, is a logarithmic scale as well. And today you just learned that pH is a logarithmic scale. So a logarithmic scale like pH basically says mathematically that the pH of a solution is equal to the opposite, and that little negative sign there is going to become important, is the opposite of whatever the log of the concentration of hydronium is. So if we have a solution where the concentration of hydronium is about 0.01 molar, or 1 times 10 to the minus 2, to find out the pH, we are essentially going to take the log of 1 times 10 to the minus 2, which you can use your calculator, or you can just figure this out because it's 1 times 10 to the minus 2. The log of this will be minus 2. The opposite of minus 2 means the pH should be 2. Likewise, if you have a solution where the concentration of H plus is equal to 1 times 10 to the minus 8 molar, and you want to find out the pH, all you have to do is take the log of 1 times 10 to the minus 8 and change the sign. So the log of 1 times 10 to the minus 8 is minus 8. When you change the sign, it means the pH should be 8. This is a basic solution. Now here's one you should confirm with your calculator, because not all our problems are going to be quite as nice as the ones that I just did for you. In this case, the concentration of hydronium is 4.6 times 10 to the minus 4. And so to find out the pH, we're going to take the log with our calculator of 4.6 times 10 to the minus 4 and then change the sign. And I think in this case, the pH comes out to be about 3.23. Now here's a little fact that most people don't realize when they start dealing with acids and bases. And that is that all acids and bases are in the presence of water. And what a lot of people don't know is that water naturally dissociates or naturally reacts to make H plus and OH minus. So that this reaction is present all the time. Every single time you have a water molecule that's in the liquid state, you will also have an equilibrium reaction with that water molecule in H plus and OH minus. Now the equilibrium constant, oh yes, this is equilibrium. The equilibrium constant for this reaction is relatively small. It's 1 times 10 to the minus 14. And this equilibrium constant is actually referred to as Kw. Not Kc, not Kp, but Kw, where the W stands for the equilibrium constant for water. And in this case, it's equal to the ratio of products compared to reactants. The products are H plus and OH minus divided by the concentration of reactants, which is H2O, but H2O is a liquid, and you cannot determine the concentration of a pure liquid. So the Kw value for water, 1 times 10 to the minus 14, is equal to the concentration of H times the concentration of OH. Now this has lots and lots of implications, one of which is that in every water solution, the concentration of hydronium and the concentration of hydroxide have to multiply together to equal 1 times 10 to the minus 14. That means if the concentration of H plus is very, very big, that means the concentration of OH is going to have to be really, really small. For example, if the concentration of H plus was 1 times 10 to the minus 2, that means the concentration of hydroxide, if my math is good, would be 1 times 10 to the minus 12. Not 11, 12. They have to multiply together equal 1 times 10 to the minus 14. Now, this does imply something very strange, and that is that means that all acid solutions, which have a lot of H plus, also have minute amounts of OH minus, which is strange for us to think about. Now let's work this back into pH. If you have a solution that is neutral, that is, it's balanced in terms of acidicness and basicness, then that means the amount of H plus and the amount of OH minus must be equal. So therefore, if I use a little equilibrium expression and H plus and OH minus are equal, I can say that X times X has to equal 1 times 10 to the minus 14. Or X squared has to equal 1 times 10 to the minus 14. Using my calculator, I can find out that X is equal to 1 times 10 to the minus 7. So for a neutral solution at 25 degrees, the concentration of H plus should be about 1 times 10 to the minus 7. The concentration of OH minus, coincidentally, is 1 times 10 to the minus 7, but that means that the pH for a neutral solution, one where H and OH are equal, the pH of a neutral solution at 25 degrees should be the log, or if I should be more careful, the opposite of the log of 1 times 10 to the minus 7, which, what a shocker, the pH comes out to be 7. Now, I keep saying at 25 degrees because, as you learned, hopefully in the last chapter, that every reaction that has an equilibrium constant, that constant is a constant at a set temperature. And this reaction for water, the Kw value for water at 25 degrees is 1 times 10 to the minus 14. Technically, if you change the water temperature, the equilibrium constant for water will change, and that will actually change what the pH is. For example, okay, let's say at some weird temperature, the equilibrium constant for water has changed from 1 times 10 to the minus 14, which is normal, to 1 times 10 to the minus 16. Now that means for a neutral solution, the amount of H and the amount of OH still have to be the same, equal, in order to make them neutral. So therefore, X squared is equal to 1 times 10 to the minus 16. Therefore, the concentration of H is about 1 times 10 to the minus 8. That means that the pH for a neutral solution at this bizarre temperature should be 8. Well, the moral of the story is that a neutral solution doesn't necessarily have a pH of 7. At 25 degrees, it will have a pH of 7. But at other temperatures, a neutral solution could have a completely different pH. Luckily for us, 99.9% of our problems will take place at 25 degrees. And unless you're told otherwise, you can assume it's at 25 degrees. There is one problem you're going to do for homework, and it says specifically, at this bizarre temperature, the equilibrium constant for water has changed. But for all the other problems, we can assume that it's at 25 degrees, even if it's not spoken, even if it's not written, and we can assume that a neutral solution will have a pH of a 7 because it will have an equilibrium constant of 1 times 10 to the minus 14.